Yeah, okay. Today I would like to start a new topic that is connected to the, let's say, to the one that we have just discussed. That is the one concerning the effects of the electron-electron interaction. This topic is just a different way to obtain exactly the same results using a different method. So I would like to, let's say, repeat the procedure using a different method, because when we will study the phonons, so the lattice oscillations in the system, and the interactions between the phonons and the electrons, there is a formalism that allows to discuss this interaction in a quite easy way. So my idea is to introduce that formalism now, when we may use that formalism to discuss a topic that we have already discussed in the past. So the new thing is just the formalism, not the result that we obtain by applicating that formalism. So in this way, maybe it's easier to, let's say, understand the use of different operators and the mechanism we use those to obtain exactly the same result using a path that we have somehow followed using these later determinants. And due to the fact that the topic I'm going to introduce you will be introduced during this class, not in a very formal way, but I will give you just the elements that are fine to understand later the phonon behavior and the phonon electron interaction. I will not think, let's say, I will include this topic into the syllabus of the solid state class, but this topic will not be a subject of questions during the examination. So if you want to talk about that, then it's fine, but I will not make any question concerning this specific topic. I will also highlight that in the discussion in the syllabus. So this is a topic that is related to quantum field theory, and as I'm not a theoretician, I just give you some details about that. The general title is the, let's say, second quantization. So second quantization is approach that is used to discuss the properties, in this case, in the solid state physics class. And the idea behind this process is the following. Up to now, the main, let's say, subject of the investigation was the electronic wave function. So many attempts have been done to find the best way to represent the electronic wave function, depending, for instance, on the effect of the lattice, on the strength of the interaction between the electron and the ion, on the strength of the interaction between the electrons and the electrons. So from now, let's say from the beginning of the lessons up to now, the question has always been, what is the wave function that the electron has when the electron propagates through the system? So up to now, the central point was to find what is the structure of this function. And when we were able to find the structure of that function, then we were also able to evaluate the energy, the velocity, and so on concerning the electron. And using this kind of approach, when we try to consider the effect of the electron-electron interaction, let's say, forced us to introduce the Slater determinant. In the case of the Slater determinant, let's say, use a single electron wave function to build up a new n electron wave function, and that n electron wave function is a determinant. So is quite a complex expression that tries to combine the single electron approach and the fact that the n electron wave function has to be antisymmetric. One of the problems of this Slater determinant is the fact that if you build up a Slater determinant for n electrons, and then for some motivation, you do not consider a system where the number of electrons is fixed, but you consider a system where the number of electrons is not fixed. Just suppose you have a solid, you shine electromagnetic waves on the solid, you make the photoelectric effect, and you remove some electrons from that. Or you consider a current or a flow of electrons that interests your system, so the total number of electrons may not be a constant of the motion. In this case, if you move from n to n-1 or n+2 electrons, you have to build up a new Slater determinant with n-1 or n+2 wave functions. So the idea is that using this formalism, the formalism based on the wave functions, then in particular in this specific situation where we consider the electron-electron interaction, if the total number of electrons changes, then we have to change the determinant. And if we change the determinant, that means that we have to build up a new structure. So it's not straightforward to consider a system where the number of electrons may change due to the interaction of the system itself with the environment. So the idea is to change the approach to the problem. And if we want to use an approach that allows us to, say, consider a system where the number of electrons may, for some motivation, change from time to time due to, again, the interaction of the system with the environment, the idea is to, let's say, not to focus on the wave function, but assume that the wave function is known. So let's assume that we have already solved the single electron problem, and we know the wave function corresponding to all the levels. So the new question is, what levels are occupied and what levels are unoccupied? So this formalism, the second quantization formalism, as an approach that is based on the question, what are the levels that are occupied and what are the levels that are unoccupied? Not what is the wave function of that level. So we assume that the wave functions and the energies of the level, we assume that the wave functions are known. And so we, let's say, in general, we are used to label the wave functions using the wave vector. So we assume that the correspondence between wave vector and wave function is known. So for any level, we know what is the corresponding wave function. At this point, we may fix an ordering of the levels. So let's suppose that we start from level 1, level 2, level 3, 4, and so on. So we represent a state of the system. Sorry, wait, this may be a misunderstanding, so please remove this. Yeah, remove this expression, it's not fine. So we have the way to represent the state of the system using this formalism is the following. So let's assume that we build up a vector, the equivalent of a ket vector, where we insert in the first position the occupancy of level 1. In the second position, the occupancy of level 2. In the third position, the occupancy of level 3, and so on, from 0 up to n, where n is the total number of electrons, but even for values that are, for levels that are higher than the level corresponding to the last electron. If we're supposed to be at 0 temperature, for instance, we know that the levels below EF are occupied, the levels above EF are unoccupied. So in this case, we have 1, 1, 1. We have one last time 1 when we consider the last occupied level. So this is the level corresponding to the nth electron in the system, and then we have 0, because the levels up to the Fermi energy are unoccupied. So for instance, at T equal 0 Kelvin, then we have this way to represent the system in case we consider that the Fermi sphere is completely filled. So we have n occupied levels, and then the other levels are empty. So in using a vector like this one here, with the specific, it's important, we have to fix the ordering. So what we call level 1 now will always be level 1 in the following. And those levels here include also the spin. So for instance, level 1 is level 1 spin up, 2 is level 1 spin down, and so on for all the levels in the system, including also the spin state. Another motivation, so if we write the things in this way, to add or to remove one electron is a simple thing, because you just need to switch from 1 to 0 or 0 to 1, depending on how many electrons you decide to remove or to inject into the system. And yeah, another problem of the Slater determinant is that in order to have a global wave function for the system that is antisymmetric, we have to build up a structure that is huge, because if we consider n electrons, this Slater determinant is the determinant of a matrix whose size is n per n. So that's a very big matrix. So this means that just to fix the antisymmetry of the system, we need to build up a huge wave function to study the system itself. So in this case, the antisymmetry is not included in the formalism. The antisymmetry is something we force from the outside by fixing the shape of the structure, of the Slater determinant. The idea of the second quantization approach is to make an approach where the antisymmetry is included in the formalism itself. So it's not something you apply from the outside. So the idea is to introduce some operators that may handle the states of the system that are built up in this way, such that the action of those operators produces a system that is already antisymmetric from the beginning. So this way, we have to define operators that are able to be applied to a state of the system that is described by a vector like this one here. And those operators have to include the specific symmetry that corresponds to the particles we are investigating. So in the case of electrons, we expect to have fermions. So the wave function of the system has to be antisymmetric. In case we have to handle bosons, then we will define new operators such that the action of those operators will build up a symmetric wave function with respect to the exchange of two bosons. But in this case, as we discussed fermions, because we are mainly concerned on the properties of the electrons, we will use the operators that, when applied to the system, build up a system that is whose state is antisymmetric with respect to the exchange of two particles. The same operators will also include the exclusion principle. That means you're not able to put more than one electron in one of those slots. I say no more than one electron because all the slots that we have here in this vector are slots that include also the spin state. So at this point, as level 1 is a specific level with a specific spin state, no more than one electron can occupy that level. So due to that, this has to be, let's say, the idea is to include also this constraint into the operators. So in this way, when you have the vectors and the operators, at that point, you may completely forget what are the symmetries and the properties of your particles, because all those informations will be included in the action of the operators. And let's say here, for instance, I have a state that is represented by a vector that corresponds to the Fermi state, so Fermi sphere, sorry. So all the levels below EF occupied and the levels above EF empty. But there is also a state that is called vacuum, and vacuum means no electrons. So vacuum is the equivalent of 0, 0, 0, so all zeros in the system. So this is the equivalent of no electrons in the system. And all the levels that we may consider as represented by these vectors are supposed to be normalized to 1. So if you make the scalar product of the vector with itself, then you obtain 1, even if you consider the vacuum state. So the main just two operators are needed to discuss all the properties of the electrons and to represent the energy, velocity, and so on of the system. And these two operators are called the creation and the distraction operators. And the name of the operator gives an idea of what the operator does. So creation operator means if you apply that operator to a state of the system, that operator will inject one electron into a specific level. So and then I will also justify this way of represent the operator. This operator is labeled as C cross I, where I and I is the index corresponding to the level where the operator is going to introduce a new electron. So in this representation, I will just, let's say, for the moment, I neglect what happens apart from level I. So I just concentrate on what happens here. Now, the idea is that this operator has to introduce a new electron in the system, but this operator has also to take into consideration the fact that we have to follow the Pauli exclusion principle. So if the state is empty, for instance, we have 0 occupancy for level I, then there is room for a new electron. So in this case, the final state will be occupancy 1 in level I. So the operator just affects the action, level I. Then at this point, we have to guarantee that two things. We have to guarantee antisymmetry, and we have to guarantee the fact that if that level had been occupied, the action of the operator would have to, let's say, we shouldn't have the opportunity to have a final value of the vector in case we already have an electron in state I. So to prevent that, here we put a coefficient that is 1 minus Ni, where Ni is the occupancy of the system before the action of the operator. So in case the level is empty, then Ni is 0, 1 minus Ni is 1, so everything is fine. If the level is occupied, then Ni is 1, 1 minus 1 is 0, so the action of the operator over that level gives you 0, so no opportunity to modify the level. We also have to include the antisymmetry, and the antisymmetry is included by this coefficient that is called theta I. Now I give you a definition of theta, then we will make an example so that the meaning of theta will be clearer. And theta of I is defined in this way, is minus 1 to the power of pi, and pi is the sum from j equal to 1 to I minus 1 of the occupancies of the levels. So depending, let's say this power here, minus 1 to pi, will switch from minus 1 to plus 1 depending on the fact that pi is even or uneven. And for the moment, please keep just the definition in mind. As soon as I have also defined the distraction operator, I will make an example of the action of those operators, so the meaning of pi will be clear from the example. So in this way, let's say 1 minus ni is to prevent the double occupancy of one level. Theta I is to guarantee the right sign to the final state induced by those operator, by that operator. So this is the creation. The distraction operator makes the opposite. So the distraction operator removes one electron in the system. So in this case, the operator is labeled as Ci, and that acts on a system, and I just consider here what happens to level I. So in this case, the idea is that the final state is expected to have an occupancy of that level that is equal to 0. Here, the coefficient is not 1 minus ni, but is just ni, because if the initial level was occupied, then ni is 1. So we have the empty level, sorry, a new state with level I empty with coefficient equal to 1. Differently, if the initial occupancy is 0, then you may not destroy an electron that is not there. So the action of the operator gives you 0, so no action. Then, to guarantee also the right sign of the final state, we have, again, theta I here, and theta I is exactly the same definition of the theta I that I used before. So these are the two operators, and basing all the things on just those two operators, we will be able to represent the same formalism that we had in the case of, for instance, electron-electron interaction, but the formalism based again on just those two operators that include both the quantum mechanical properties that we expect the overall state of the system has to have when we build up the state itself. Before going on, I just make one last definition, and then I'll make the example. If you just try to see what happens when you apply C cross psi Ci to a system. So for the moment, I put here just Ni. So for the moment, I don't know what is the occupancy of that level. The first operator that acts on the system is the distraction one. The distraction one gives me Ni, that is the initial occupancy, then theta I, and a state where here I have 0. Because if initially Ni was 1, then if the initial occupancy was 1, then the action of the operator destroys that electron and gives me a new state where just that electron is missing, and the coefficient here is 1. If the initial occupancy was 0, at the end, no action of the operator due to the fact that you may not destroy a state that is not there. When you apply C cross I, at this point, we have that C cross I gives us 1 minus, please keep in mind that now I'm going to write down Ni, but this is not, let's say, I just write the value of Ni because now I know that the occupancy of the level is 0 because I have just applied the distraction operator. So here I have 1 minus 0. Then I have Ni that was there after the action of the distraction operator. Then I have another theta I. So for the moment I have theta I times theta I, and then I have a state with 1 electron in position I. So this product here, theta I times theta I, gives me 1, because irrespective of the sign of theta, then the product of theta, the theta to the power of 2 is always 1. Then I have another one here, and here I have Ni. Ni was the initial occupancy. So due to that, if we apply C cross I, Ci, we go back to the we may go back to the initial state of the system, but in this case, the coefficient of the vector is equal to the initial occupancy. So the idea is that if we apply the construction operator and the distraction operator in this order, then we may go back to the starting state having a coefficient that is equal to the occupancy of the initial state. So this combination C cross I, Ci, is called, is the operator Ni. I put the hat just to say that Ni is not a number, but is an operator, is the number of particles operator. So if I want to if I want to know what is the number of particles that correspond to a specific level, I evaluate the C cross index of the level times C index of the level, and I apply that operator to the state of the system. And in this way, at the end, I find the occupancy of the level I'm interested in. And just to make now an example, so to understand in a better way what is the meaning of that theta that can be applied to the system, I suppose to apply two construction operators. So I suppose to apply C cross I, C cross J. So I want to inject 1 electron in level I, 1 electron in level J, and just to, let's say, be sure that I have room for those 2 electrons, I suppose to inject those electrons in vacuum. This is just to simplify the calculation, but the result is exactly the same if in place of vacuum we use another state. Since the ordering of the levels is important, I have to assume what is the order of the levels of level I with respect to level J. I assume that, but then this choice is, let's say, has no impact on the final result. I assume that level I, that using the ordering that I apply to the levels, level I appears before level J. So in this case, when I apply C cross J, I have a new level. I have 0 electrons in level I, 1 electron in level J. In this case, when I inject this electron here in level J, P corresponding to J is equal to 0, because the sum of the occupancies of all the levels that are found before J is 0. So due to that, theta J is equal to 1. Then when I apply the construction operator, I have the coefficient 1 minus initial occupancy, and in this case, the initial occupancy is 0, so the coefficient is 1. So I have 1 due to theta j, and 1 due to the 1 minus initial occupancy coefficient. When I then apply C cross I have occupancy of level I equal to 1, occupancy of level J equal to 1. In this case, PI is equal to 0 because the occupancy of all the levels before I is 0. And so also in this case, the corresponding theta is equal to 1. So I have 1 times 1. So at the end, I have a vector with electron I and electron J, and the occupancy of the levels is 1 for each level. I now exchange the order. So I exchange the order of application of the operators. At this point, I apply operator C cross I. So occupancy of level I equal to 1, occupancy of level J equal to 0, PI is 0 because the occupancy of all the levels before I is 0, so theta I is 1. So in this case, I have 1 for theta J, for theta I, and 1 for the coefficient due to the initial occupancy. The initial occupancy was 0, so 1 minus 0 gives me 1, just 1. When I now apply C cross J, I will have a state where level I, is occupied, level J is occupied. Now, Pj is 1 because there is one level, there is one electron in a level that is smaller than J. So Pj now is just 1. So theta J is minus 1. So the coefficient here is minus 1 due to theta J times 1 because the initial occupancy of level J was 0, so 1 minus 0 is 1. So in this case, we obtain exactly the same, let's say the final state is always the same. But in this case, the final state has a minus sign in front. So if we exchange the order between two electrons, then the sign of the state switches from one to minus 1. Now, as you may, let's say, imagine now, even if the occupancy of all the levels that are not I and not J had been different from 0, in this second situation, Pj would have changed because with respect to all the occupancy of all the other levels, a new level was introduced here. So we, let's say, if we compare this situation with many occupied levels, with many more electrons in the system, we would have obtained exactly the same result. So a change of sign due to the fact that the value of P would have changed by 1 because one additional electron would have been injected into the system. So the full calculation would have been slightly more complicated due to the fact that, again, we should have included many more electrons would have been included in the calculation, but the final point would have always been the fact that the change of sign, the change of one of the coefficient corresponding to P, and due to that, the change of sign of theta. Please note that the position of the electrons is always the same. So you may not actually exchange the two levels because we have fixed the order from the beginning. So even if you say, I exchange two electrons, due to the fact that we force an ordering of the levels, it will never appear that electron I and electron J will be switched, will be exchanged. So the ordering will be always the same. We have just exchanged the order of application of the creation operators. And the fact that C cross J produces a state whose sign is opposite to the state that is produced by C cross I, means that if we consider this expression, the sum of those two operators produces two states that are the same state with just a different in sign. So this sum is equal to 0. And this is maybe written also as the anticommutator. So C cross J anticommutator is equal to 0. And using exactly the same approach, it is also possible to see that Ci, Cj, so the anticommutator between the creation operators is equal to 0. And one equation, let's say, one additional relationship that we will need for the calculation is this one here. So the anticommutator between a creation operator and the distraction operator. And in this case, what you have is delta ij. So this is a Kronecker delta. To be more precise, I should write Kronecker delta times identity. So that Kronecker delta at the end represents an operator. So this is 0 when the coefficient when level I and level J are not the same level, and is different from 0 when I and J correspond to exactly the same, exactly the same level. Okay, so for the moment, we have just defined those new operators, and the only thing we need to remember from now on is let's say we will mainly refer to from now on we will mainly use just the commutation rules between the operators. So those commutation rules will be important, and we will also use the fact that, as we have seen before, the sequential application of creation and distraction operator gives us the number of particles operator. And I just introduced something that will be useful later. How may we estimate Ni? So in general, how is it possible to estimate Ni? Ni is the occupancy of one level, and the occupancy of one level is represented by the distribution corresponding to the particles we are investigating. So as now we are investigating electrons, we may use the Fermi-Dirac distribution function corresponding to level I to estimate the average value of Ni. So from now on, one of the things we will try to do is, on one side, to use the commutation rules between the operators to simplify any expression we will have to consider. And at the end, what we will try to do is to arrange the operators so that the number of particle operators may appear into the calculation. because if that operator appears into the calculation, then we will be able to substitute, to obtain the expectation value of that operator over the state of the system, and that expectation value is the value that the Fermi-Dirac distribution function has when we consider the level with index I. So the Fermi-Dirac distribution may be considered to be the expectation value of the number of particle operator corresponding to a specific level into the system. So at this point, if we are able, with these rules here, we expect to be able to transform any possible combination of those operators into something that may be evaluated, but just by knowing again the expression of the value of the Fermi-Dirac distribution function. And yeah, just a final comment, then I make the break. For the moment, I have called the creation operator with C cross and the distraction operator with C. This is a formalism that resembles the fact that you may, the cross is in generally used when you consider the adjoint of an operator. So the idea is just to see that actually C cross and Ci are one the adjoint operator of the other. And for instance, if you, let's say, just to simplify the notation, I just write K as I just write K, the state where all the electrons are, all the levels are empty and just level K is occupied. But this is just to simplify the problem. In general, you may also use a more complex vector. In this case, as the vectors are normalized, this is equal to 1, then you may consider vector, the level where the level K is occupied can be considered to be the result of the application of C cross K to vacuum. So in this case, if I now use the, let's say, CK is applied on the cat. If I now I want to find the adjoint operator, so I want to apply the adjoint on the bra, then here on the cat, I have vacuum. So let's say to have 1 as it was at the beginning of the calculation, I should expect to have vacuum also on the bra side. And to have vacuum on the bra side, the only solution is to, let's say, destroy K. So to destroy the electron in level K using the CK operator. So in this way, we have vacuum, scalar product, vacuum. So we have again 1. So in this, and you may do exactly the opposite if you start from if you start considering this product, then you may evaluate, you may say that vacuum is due to the application of the distraction operator over level K. And at this point, since you have K on the cat, the only solution to have 1 is to have K also on the bra. And K on the bra maybe it's not the best way to write that, but can be expected to be obtained if you apply C cross to vacuum. So due to that, again, you may consider that the cross for the formalism of apply the cross to the construction operator is just because one, the distraction and the construction operators are one the adjoint of the other. Okay, and Yeah, I think that those are all the definitions that I had to present you in order to introduce the actual operators that we will use for the calculation. So if you have no comments or questions or anything to ask concerning this part, I will make the break and then I will go on with the discussion after the break.
No questions, thank you.
Grazie.